Hey Darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters, and here we are. This is episode 4 of this voyage, the physics of dart flight. And I couldn't resist having a go at that amazing checkout that sealed Jan van Veen his first major title last night in Dortmund. What an amazing final between the young gentleman and Luke Humphries, the world number 1. And in the deciding leg, Jan got that 100 checkout, 20 treble 16, double 16. Just amazing scenes. And it's that kind of thing, you know, great sportsmanship, a really good match, all, you know, just really, you know, it's what we love in darts, isn't it? Right, so what's on the menu today then on this voyage? Well, we're going to talk about the Goldilocks angles, the special angle of release that I believe every dart player should, excuse the pun, aim for, have as their ambition as they play darts. So what I'm going to do is turn this board light off and just do a really quick recap of how we got to where we are right now, and you'll find this a very straightforward video to understand today, following on from the previous one. So if you recall then, we first of all went into outer space because, as I said at the very beginning, the dart has two forces on it. It has force of gravity pulling it down, and it has air resistance pulling it back. And in outer space, in a vacuum, we could get rid of both forces. No air resistance because you're in a vacuum, and no gravity. And of course, not that surprisingly, the darts travel in straight lines. Now, in the previous video, in episode 3, we came back down to Earth, but we still had our oxygen masks on because still in a vacuum, all right? So we're in a vacuum chamber on Earth playing darts where there's no air resistance, but now we have the force of gravity. And I went through that quite carefully, and the key point was taking, if this is the dart here, so the key point then is that this dart has got a velocity at some instant in time. And remember, the velocity is the quantity that has a speed. So the size of this is the speed, but it also has a direction, which the arrow indicates. But the key point is that you can split that into a vertical piece and a horizontal piece. So you can talk about a vertical piece of that velocity and a horizontal piece of that velocity. And according to Newton's second law, Newton's first law says that if there's no force acting, the velocity is constant. So in the horizontal direction, there's no force acting in a vacuum horizontally, because the only force is gravity, and that's operating straight downward. So this experiences no force, and so the horizontal piece will just continue at a constant horizontal speed. The vertical piece, though, of course, will experience gravity, and what we then can understand is that we can divide our motion up. Let me try and draw a picture. A typical trajectory then, we can divide the motion up into a constant horizontal piece. So the horizontal piece just goes at a constant speed in this direction, and then the vertical piece is like throwing something up in the air and then catching it again. It just goes up, slows down, and then it speeds up as it comes down. Okay, so you've got this kind of up and then down motion going on in the vertical direction, and when you combine that, so going up and then coming down again, that gives you this shape, which is called a parabola, and that is the shape of a projectile in the absence of air resistance. Now we're going to talk about air resistance in the next video, which will be probably the last but one in this series, and that's going to be quite a complicated thing, but I'll just give you the basics of that, and it won't change. It's quite hard to understand, but it won't actually change our results that much, to be honest. It's just a right pain to calculate. One key thing is, though, that this shape does not depend on the mass of the dart, on the weight of the dart. As long as you always throw the dart with the same initial speed, this shape will be true for any weight of dart, a Ryan Searle dart or a Stephen Bunting dart from years ago when he was throwing an 11-gram dart. And you might say, well, why is that true? Well, it's because, as I mentioned, the change in the motion that comes from applying a force from Newton's second law. So Newton said that force is equal to mass times acceleration. If the force is due to gravity, well, the force due to gravity is actually the mass of the object times this constant that we've all seen, 9.8 meters per second. So if that's the force due to gravity, and this is the mass, and this is mass times acceleration, what you can see is that the mass cancels out. So the acceleration due to gravity is the same for any object, regardless of its mass. Now, the reason we see things depend on mass a little bit in real life is because of air resistance, but right now we're in a vacuum, so mass will only enter into this when we take air resistance into account. Okay, that's assuming that you always, these different weighted darts get started with the same velocity. Okay, if you put the same thrust into every dart, then the heavier ones will actually have a lower velocity when they start. That's a different thing. That's up to the player about the amount of thrust that they give the dart. I just wanted to clear that little point up there. Right. Now, the key thing then that we're going to be talking about today is the angle of release, which is the angle of the initial, and we call our angle theta, remember, that Greek letter which everyone in science and maths uses for angle is this letter theta. That angle of release, we want to vary that. And you might remember in the last video I said that if you wanted to maximize the range, so imagine this is actually a cannon rather than a dart player, so we actually just have a cannon here, okay, releasing a cannonball. Then if you wanted to maximize the range of your cannonball on a level ground, the magic angle is 45 degrees. That gives you the maximal range. And you might say, well, why is that true? Well, if you have a steeper trajectory, you can imagine the trajectory will be like this. And if you have a shallower trajectory, it's like this, and the cannonball will just hit the ground here. So to get the maximum range for a cannonball on a level ground, 45 degrees is sort of a special angle. And I want to get the idea of a special angle now, but let's keep with the cannon, but let's change the scenario. Let's say that now you have a cannon and you've got a siege. So this is all pretend, because I really don't like the idea of firing cannonballs at cities. But let's say in the, 200 years ago, you've got a siege and you've got a wall that you need to knock down with your cannon, and it's at a different height to your cannon. Okay, so let's say our cannon is over here, and let's say the target is over here at a different elevation. So maybe you've got some rugged ground here and you've got some sort of fortress here, some tower, okay, and it's at a different height. And we're going to ask a slightly different question. We're not going to ask how far can I fire the cannonball. What the question we're going to ask is, if I set the angle of the cannon, how fast, how much power do I have to give that cannonball? What must the initial speed of the cannonball be? Okay, so let's just have a little think about this. If, first of all, there's a straight line between the target and the cannon. So if we set the angle of the cannon to be parallel to that straight line, I actually need an infinite amount of energy for that cannonball, because basically any gravity at all, any force on it is going to take it low. Okay, so you sort of need an infinite speed of that cannonball to hit the tower. It actually won't hit the tower, even if you give it you know, as much as you possibly can. It's just going to dip below. So there's going to be a minimum angle anyway where you have any chance of hitting that target. If I have a cannon that is in a very vertical sort of orientation, in order to get to this, and you can imagine this, imagine someone says you've got to throw this rock and hit that target, but the rock has to be thrown 30 feet in the air. You think, well, how am I going to get it there if I have to throw it high? I'm going to have to give it a huge amount of power. So you need a lot of power for shallow angles, and you also need a lot of power for large angles, because this has to go way, way, way up in the air and then finally come down and hit the tower. And if it's a shallow angle, it needs a lot of power just to somehow stave off gravity to hit the tower. But there's going to be a Goldilocks angle where you need the least amount of power to hit your target. Okay, so there's going to be a Goldilocks angle, and our remaining color is red. There's a Goldilocks angle here where you have the hit your target with the least amount of power of that cannonball, or the least amount of the initial speed of the cannonball. And so you can make a graph of this. If I say, as I change those different angles, and there's a minimum angle where I need like an infinite amount of energy, and I'm gonna plot the speed here of the cannonball initially. So the initial speed, what we're saying is, if you have shallow angles, you need huge amount of initial speed. If you have high angles, you need a huge amount of initial speed, but there's a Goldilocks angle which has the least speed. And so if you made a graph of this, if you worked out what that initial speed is for every single angle as you vary that, you could plot a curve and it will look something like that. Okay, and that is the Goldilocks angle. All right, sorry, I'll get back into the camera view. That's the Goldilocks angle there. Why is this important? Well, I think that the Goldilocks angle is the angle we all need to aim for. Silly saying the word aim when we're playing darts, but we need to aim for that Goldilocks angle because it's the least effort, you see, in our action. And I think when we talked about the philosophy and strategy of darts technique, we talked about naturalness and smoothness. Everything in nature is smooth typically. Nature likes to minimize energy and have everything as smooth as possible, and that's how we should be with our dart throw. So we need to find this angle, but that angle is going to depend on the height of the target. If this tower were lower or higher, this special angle would change. So let's go back and draw our matchstick dart player and just get a feeling for all of this in terms of the no more cannons and towers and sieges, but a game of darts. So let's do a really quick sketch of our setup. We've got our gentleman playing darts here. Pretty used to drawing him by now. Okay. He's legal, he's standing behind the oki there, and then we've got the dartboard here. I've got to get this right here. So someone told me if they're 6 feet something, their eye is in line with the bullseye. So that's a fairly tallish dart player there. There's the dartboard. And we defined lots of things, didn't we? We talked about the length of the forearm. We talked about the height of the elbow above the ground. We talked about the distance of the elbow from the board. Okay. We talked about the height of the target, and that's going to be very important for us, the height of the target. And then the angle of release of the dart here, okay? And also the speed of release. So what makes this harder than the cannon situation is, whereas the cannon just has to tilt to change its angle, we move our arm, and that means that we change the distance between the dart and the target as we move our arm. and we also change the height of the dart. So this is a harder problem. You can solve it for the speed of the dart with respect to the angle of release. And I'm just going to show you the result, just because to show you that you can do it. So that's the result in terms of all the things that we like. You know, D is the distance between the elbow and the board, L is the forearm, HE is the height of the elbow, HT is the height of the target, G is acceleration due to gravity, theta is the angle of release, and U is the speed. That's the formula. And if you plot that formula, so I've taken my measurements for my favorite stance, and here's that curve that I talked about. This is for the treble 20. Okay, so you can see that there. So I just get it into view there. So that's my curve for the treble 20, and you can see it has just that shape I talked about. And if you can see there at the bottom there, the special angle is just below 45 degrees. So that gives me, for my measurements, quite an interesting thing, that for me, treble 20, the Goldilocks angle is around 45 degrees, which is kind of a special angle in ballistics, because that's where you get the greatest range if you have a flat, playing field. So that must mean that when my dart is released when I'm aiming for treble 20, it's at almost the same height as the treble 20. But if you're a much taller player, if you are a more diminutive player, if you have a different stance where maybe you lean or you have a very straight back, all of these things are going to change. And we now start to see how all of this stuff on projectiles and actually working all out gives us, each player, a kind of, what might you call it, like a unique signature of what are their Goldilocks angles for different targets. Okay, so as we change the target here, so let's say this is me for treble 20, we just saw that my Goldilocks angle is around 45 degrees. Let me get a different color pen. So my trajectory would be something like this, 45 degrees. And then if I'm going for double 3, I'm going to have a shallower trajectory if I want to get this Goldilocks angle again. Okay, something like that. And if I wanted to go for tops, slightly higher trajectory. And so here are, this is again for me, for my favorite stance, these are the curves for double 20, treble 20, bull, treble 3 and double 3. So I'm just going down the board to key places. So what's my Goldilocks angle for double 20, treble 20, bull, treble 3 and double 3. Now we never go for treble 3, but it's pretty much next to that treble 19, so that's pretty much going to be the same thing. Same with double 3, that's a double that sometimes crops up, and you sort of do need to practice that one. It's no one's favorite, of course. But what you can see is that I've marked where those Goldilocks angles are for each of those curves, and you can see how they fall on a straight line. So that line there that goes down there is how my Goldilocks angles change with the target, and also how the initial speed of the dart. So you throw it slightly harder for the tops, of course, and less hard for double 3. So these are, I think, what every dart player should aim for, is to be throwing on this curve. But you could say, no, I'm always going to throw at the same speed. And you see, if I throw at the same speed, that line will cut through all these curves, and I just have to choose my angle. So I could throw at a higher angle for each of these targets, would always have the same speed and just have these really high angle. Or you could have really fast, shallow darts. But to me, doesn't feel right from a science point of view, because you're putting more effort in, and what these points tell you are these are the least effort, the least action, as it were, points for the different targets. So that's kind of what I wanted to get across today, is that we're really now starting to see how we can bring all of this physics back to the dart player, because no one else in the universe will have these same points that I've got, because, you know, it depends on the size of my elbow, depends on my height, depends on my stance, depends on my action. Okay, where exactly, the key thing is where that elbow sits, all right? So what we're going to do for the rest of the series then is, in the next video, we're going to take into account air resistance. Now, I should just say, by the way, you can't find these Goldilocks angles, unfortunately, exactly. You have to use a computer. So I've got a short computer program that works these out for me, okay? And when we add air resistance, it gets unbelievably messy with the maths, okay? I mean, it makes this look like a walk in the park when you add air resistance. It's so much more complicated, but you can still fight your way through it with the physics, okay? Which is what I've done. And I've got a computer program that does everything with air resistance too. But I want to go through the physics of air resistance in the next video, because it's really interesting what's going to happen to these trajectories. What we're going to find is they're going to dip at the end. And also those trajectories will now depend on the weight of the dart, okay? But finally then, we're going to have these curves, but including air resistance. And that is kind of gold dust then, because that's telling us these magic angles, these Goldilocks angles for a given player. And what I think I'm going to try and do after this series has ended is take measurements online from photographs of famous players like Luke Littler, or now Jan van Veen, he's now a famous player, and say, well, what are their Goldilocks angles, and what's their sort of magic connection between speed of release and special angle? And my gut feeling is that players are going to fall into different kind of categories, different kind of classes, depending on basically instinctively how they throw the dart. I think the elite players will naturally fall into certain groups. So that's what we're going to get to in the future. All right, so let me end there. Again, what a brilliant final last night, and huge congratulations to Jan van Veen, and huge congratulations to Luke Humphries for being such a brilliant sportsman and so gracious in defeat. Wow, what a role model he is to young players. So 3 darts at the Oki, make them count. I hope you're all doing well, and I'll see you soon.